some way of comparing one logic to another. And the traditional answer, as I say, is to say, well, I compare this logic to another by establishing a homomorphism that respects all of the connectives, right? And here, yeah, yeah. And from my point of view, this a relational view makes more sense for the following reason. If I have two languages in which I'm describing different but related domains of interest, I see no reason whatsoever to think that every sentence in the first language has a simple translate. In other words, I speak to Marco all the time, and I know this is not the case between Italian and English. There's not one sentence that translates an English sentence into Italian. It requires, well, it's even worse when we're talking about Marco. But even between real English and real Italian, it's unlikely that a single sentence in Italian will suffice to translate a single sentence in English. There's no reason to think there's a homomorphism, for sure, right? But even worse, there's no reason to think that there's a functional relation that is translation. Instead, what you would expect is that an individual sentence in English may require an entire paragraph as a translate. In other words, there's a relation between the sentences of English and Italian, certainly, but there's no reason to think that relation is simply a functional relation, right? So a way of so if we're talking about translating between languages that are logics, in other words, that each one has its own entailment relation, then it seems to me it makes a lot more sense to think about it this way. Yes. Well, it's a functional relation to the power set of the other thing, right? And in fact, it might not even. I even take a more dialectical view of this, which is that I translate, and then you say, "Well, I didn't quite understand it," so now I elaborate, and so it might not even make sense to think of it as a function to the power set. It might be something that's much more conversational. So that if I say this sentence here entails that sentence, this sentence of English entails that sentence of Italian, you might challenge me, and I might have to give you better evidence. In other words, a better translate. Yeah. No, this will be pretty much just technical aspects of that. But I'm just giving you a motivation for why I think this kind of relational view first is one that makes sense. What we're trying to do is think about what Evan's going to talk about later today, domain-specific logics and how we compare them and how do we deal with the interfaces between logics. It seems to me that a functional interface is not quite as rich and as frankly as useful as this kind of relational interface. That's kind of the idea. So a weakening relation, which Alex alluded to earlier this morning, essentially the same idea, but he was doing this in a quantology setting, is a relation that has this property, that if I have an entailment in the first logic, this arrow 0, and an entailment in the second logic, if I can compare something in between, then I can weaken the statement. So in other words, phi entailing psi comes from the fact that it's a weakening of the original statement in the relation. So that's where the word weakening comes from. It's basically the weakening law of proof theory. Yeah, that's just my pedantic way of putting the primes in the places I think they should go. Yeah, exactly. It's a generalization of transitivity to having three separate relations now that have to interact with them. In two different languages. They may be, yes. Right. So the comparison of the languages is the turnstile. And the internal inference, the internal entailment is arrow 0 versus arrow 1. And the comparison relation is the turnstile, right? And for the category theorists in the room, if these are simply quasi-ordered sets, which is what the arrow is really saying, if it's transitive, then these are profunctors on those things as categories. That's what a weakening relation is. And I don't think Alex said that, but the same thing was going on with this quantum arrangement. You can interpret those things in a profunctorial way. It comes from the weakening rule in Gensen calculus, that if I have an entailment and I either strengthen the premise or I weaken the conclusion, then it's still an entailment. So that's where that phrase comes from. And I think I get credit for coining it as a separate concept, but it's kind of owned by the community at this point. But people call it weakening relations. Jose. Well, no, I'm not presuming that there's an interference, but if there is, then it's an inference in this direction, not the other way around. Yeah. Well, so I'm saying that if phi prime um, entails psi prime, these are in separate languages. Think of psi prime as being sort of a weak paraphrase of phi prime. So phi prime entails psi prime, meaning that psi prime is some kind of reasonable approximation of phi prime. And then if I strengthen phi prime to phi, if I weaken it, and if I strengthen the conclusion, then I still have another intent. That's the intended. That's right. That's the idea. Is that the turnstile is meant to be a consequence relation, but it's between separate languages. And this is more or less the least you could expect from that situation. Right? So that's why they're worthy of investigation, because that is kind of the weakest situation they have. Right, two entailment systems. That's right. And then what I want to count as some kind of weakening relation is a way of paraphrasing sentences in one language into the other language. Right. 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 That's right. Right. So that if I can make a stronger inference in English, it will still entail the same thing, the same translate into Italian, the same paraphrase into Italian. Yeah, that's the basic idea. So so the goal today, though, is some technical things that I think will be interesting to the Topos Institute folks. It is to take these relations seriously and find a way of basically try to build an analog of what's known about calculuses of relations, categories of relations, and how they are related to what are called regular categories. That's a very classical idea. I know several people in the room are very, very familiar with. Some of them have written very nice papers about that relationship, things like that. Brennan and Spivak actually have written a very nice sort of pedagogical paper on that area, very nicely done. So what I want to do is the analog of that paper. First notice that the categories of weakening relations is this one that I just described. But we could take a more general view and say, well, what would be a category of relations? What would that mean more abstractly, rather than the concrete one that I just described, of partially ordered sets of weakening relations? Well, what would that look like in a more general setting? And how can we make a relationship between those things whatever those will turn out to be, and what are called order regular categories. That's also an idea that you might not be completely familiar with, so I'll introduce it a little bit. It's actually something that Alexander and Eugene Belleville developed maybe 15 years ago or so, something like that. So what I'm going to do is try to set up the right analogy between regular categories and categories of relations, which is the classical theory that people know, and order regular categories and X, something that would be sitting in that corner of this analogy. Yeah, in the concrete setting, yes. Yes, that's right. So this is just showing you, this is just suggesting that there is a concrete category that I'm aiming as the kind of intended model. But I want the abstraction of how categories should interact with one another in order to make sense of it. And there are other situations that have similar structure. For example, if I have the category consisting of meat semilattices and what are weakening relations that have this extra property, namely they respect the meat, but they only need to respect it on the right-hand side of the relation, because on the other side they're basically respecting it for free because they are meats. And frame relations have a similar structure, but they have to respect the arbitrary joins that are coming from the other side. So those are reasonable categories that we would like to investigate. If you're interested in semilattices, these would be translates for semilattices. If you're interested in frames, it would be the same thing. In other words, all I'm suggesting is that there are a family of categories that should fall under the same theory, because those are all examples of order regular categories. The underlying semilattices and so on. Distributive lattices also form basically anything that's a variety in which the objects have an underlying order will give you an order regular category. So here's the classical thing, right? So it's an ordinary regular category is a category that has finite limits. It has a strong mono factorization system. I probably don't need to tell you all the details of what that means. You know what a monomorphism is, and a strong. It's an epimorphism that just has some nice factorization properties that many of people in the room already know, and I'm not sure it's terribly important for the technicalities. Anyway, these things that are called strong morphisms, strong epimorphisms, are preserved by taking pullbacks. And what that gets you is, well, that for one thing, any algebraic quasi-variety is automatically a regular category. So in other words, there's a huge class of models for this. And it's interesting. It's even better. Any regular category that has free objects in it essentially is a quasi-variety. So regularity is getting very close to the notion of a quasi-variety. It's just the freeness is the only extra feature that you need to go from regularity to being a quasi-variety. That's for the algorithms. That's that connection. All right. That's all just to say there are lots of examples of this phenomenon. And that's one of the main reasons why we studied, although that's not the original motivation for thinking about it. Well, actually, before I say that, for those who are not so familiar with the algebra language that I'm using, regular categories are also characterized as the categories whose underlying logic is essentially the fragment of first-order logic involving positive sentences with existential quantification. Those are regular sentences, and theories made from implications between regular sentences are regular theories, and categories that can be axiomatized by regular theories are regular categories. So there's all these really nice connections between logic, algebra, and category theory. That's regular categories are one of those places where all three of those things come together in a very nice, satisfactory way. So what is a relation in a regular category? It's going to just be what you typically think of as binary relation. It's a set, if you want, with an object in the category and two legs, right? And it's should be jointly monomorphic, that's basically saying it's a subobject of the product. Saying it this way, it's a little bit of a fudge, because all you're saying is that I don't really care about the existence of products in this definition of a relation. But on the other hand, regular categories are kind of limits, so I might as well have said it in terms of product. So it depends on your taste, whether you care about saying it that way or not. At any rate, it's these spans that are the things that are encoding binary relations, right? And now we can define a relational composition that I'll write with a semicolon there. Basically, what you do is you take these two spans. Maybe I can write it real quickly here. So I have two spans that look like this. So a relation here, a relation here. Now what I'll do is I'll just make this square, which is a pullback. Roughly speaking, that's the category theorist's version of an intersection. That means that this leg and this leg, I want them to encode a new relation, right? But they won't, because with this, there's no guarantee that that's monic. So what I have to do is use the strong the strong mono factorization to say that, well, that means that I can factor this thing. Oops, put the wrong symbol there. So I can factor that leg and that leg together simultaneously to look like this, so that now I have two legs that are mono. That defines a composition, right? The kind of important point about that is that the composition that I just sketched over there is associative if and only if the strong morphisms of my category are stable under pullback. So you take all the other axioms, having finite limits, what have you, and the stability under pullback is the thing that guarantees associativity of this composition, right? So in other words, I get a category if I have stability under pullbacks, right? If and only if. So that says that, well, now regular relations automatically give you a category, sorry, a regular category automatically gives you a category of relations with that composition that I just described. And in concrete categories that you are familiar with, that's the composition you were expecting, right? It is relational composition. Okay. And it extends in nice ways. And again, all of this is completely classical theory that's been very well worked out for a very long time. So I'm not telling anybody anything new so far. Now, what is the structure of these rel categories, though? What is the structure of a category of relations? It turns out that they have a very nice characterization as well. Any regular category, the category of relations is, I know I'm throwing some jargon at you, and sorry, I'll describe the Frobenius thing in a little while. Tabular says there's a certain kind of factorization of relations into functions. And the Frobenius axiom says, roughly speaking, that the objects in your category are discrete objects. They don't have their own underlying order. The Cartesian bicategory, I'll show you in a moment what that talks about. So this is kind of just reviewing the classical stuff that we know, right? Every regular category comes with this rel category, and the rel category has all the features that I've listed there. So one of the things that I mentioned was that the rel category is a Cartesian bicategory, and that's a category that has a monoidal structure. If you're thinking about sets and relations, that's Cartesian product, but in the category of relations, that's not the categorical product. And you can really write these things in a very satisfactory way using wiring diagrams. It looks sort of like this. Composition just means sticking two wires together. And the monoidal product operation in the category just means stacking. And it's really quite satisfying to see how cleanly that works out. And the axioms, these are axioms now, for Cartesian bicategories, basically say that the wirings work this way. Yeah, I don't know if you want me to go through some of these details. I suppose I can, but basically what we have is something like associativity laws. Those are the ones that are in the middle. We have the fact that I can kind of slide these are morphisms. So the wires are objects and the boxes are morphisms. And this basically says I can move a relation, so to speak, across. If you think of it concretely, I can say, give me an input to a relation and give me perhaps multiple outputs from here, and then I copy the output that I got. Or I could take the single input and copy it and then run it through the relation, and that will be a weaker relation by having done that. So that's why it's a less than or equal step. So if you sort of sit down with a napkin, you can see that all these things just work out. Right? That's the way they should work out. Anyway, so these are the axioms that we use for Cartesian bicategories. Right? And then the Frobenius axiom is this little funny guy that says that, again, if you sort of run through what this is telling you, it's basically saying that if I push an element in through one of these wires, and the split means copying it, and then the merge means they have to agree as they go back out, then this basically says there can't be any order on the elements of the underlying object. Again, a napkin at lunchtime, I can explain why that is. So now the theorem here, this is again just a classical theorem, is that a tabulated Cartesian bicategory is a category of relations if and only if this little funny axiom holds, this Frobenius axiom. And that's an important theorem because now we actually characterize categories of relations. And there's a really nice exact match between regular categories and categories of relations. It's exactly via this discreteness. Now the trouble is, for me, that the categories I'm interested in fail this axiom. Right? They just have to. Because the underlying objects are ordered, they're going to fail to have a Frobenius. So what I need is to find some way of fixing that. Because all the categories that I've mentioned, rel pos, rel semilattices, rel frames, and so on, they are Cartesian bicategories. But they fail this Frobenius axiom. Uh-huh. Oh, I don't know. So this goes from A through B to nothing, right? To the empty diagram. The empty diagram corresponds to the unit of the monoidal structure. So, right. So the categories I'm interested in, these categories of weakening relations, and from other varieties like semilattices, they fail Frobenius, but they have almost all the rest of the structure that you want from a category of relations. This entire bicartesian category structure is still there. So you need to start looking for, well, if we can't use regular categories, then what should we use as the analog? And just as luck has it, I guess, one of my colleagues, Alex Kurtz, wrote this really lovely paper with Yuji Velido, describing order regular categories. And you can see, you can kind of compare the definition here. Those of you who remember the definition of regular categories, it's almost the same, right? In fact, there's one thing that changes. You have to take all finite weighted limits instead of just all normal limits, ordinary limits. You also have a strong mono factorization system, but you have to interpret strong and mono in the ordered setting. But once you do that, it's exactly the same definition. And once again, the strong morphisms are the ones that need to be stable under pullback. And strong morphisms are effective. don't worry about that. That's a little technicality. But basically, it's saying that strong morphisms are the same things as regular evidence in the right or in the ordered set. And their paper really investigates these from the point of view of order quasi-varieties. So they say, well, what would it mean to have a free object in these things? And when you do have a free object, you indeed have an ordered quasi-variety. So their theorem is very much analogous to the classical. So categories like semi-lattices, frames, distributive lattices are all examples of order regular categories. Boolean algebras are not. And that's because in the signature, you have this antitone operation of negation. So that doesn't work there. Hating algebras are right. Right. So again, this is a paper from about 15 years ago, describing these order regular categories. Now, in my setting, I need to think about two different kinds of composition. So composition, where I'm using a fat semicolon there, takes the same situation. You take two relations that are defined this way, and instead of using a pullback here, you use a comma. A comma meaning that if I follow this leg, that's less than this leg. And it's universal with that property. That's what a comma is. So it's exactly the same idea as a pullback, except that it's now with respect to an order instead of with respect to equality. But same definition. So I form my two new legs, and then again I use the factorization system to make this into an epimorphism followed by a monoid. So that's my new composition by way of commas instead of by way of pullbacks. And the original basic composition still makes sense because I have all finite limits, so I also have pullbacks. So the small semicolon means make your composition by taking a pullback and then factoring, and this means take a comma and then factor. And it's very easy to see that that relation holds between those two things. You just have to sort of write it down. And it makes sense. And what isn't so obvious is this sort of funny associative law. But it works. You can figure that one out for yourselves. Okay? But now the trouble is that the diagonal relations are no longer identities for this new composition. But because basically taking a pullback of a diagonal with a diagonal is still a diagonal, but taking the comma between these two things will no longer be that. So we don't have what we think we have. On the other hand, it actually works out pretty nicely. Sorry? Yeah, next page. This is the nice thing. Well, I guess I don't say it here, but I will. Yeah, okay. Maybe I put it on the next slide, but I'll give you the answer to your question very quickly, is that diagonal fat semi-diagonal is the weakening closure of the diagonal. It's the smallest weakening relation that contains the diagonal. So in other words, it's the order on the object you came from. So you can actually find the underlying order in pause. But in category theoretic terms, that's sort of the right thing to recapture the order on the object. Mm-hmm. Yeah, that's where the name comes from. Yes. Yeah. So now this secondary justifying theorem, which is similar to the one that I had for regular categories, says that, well, first of all, basic composition is still associative. Strong morphisms are stable under pullback, which you have to do some work to prove, but it's in fact the case. These are order strong morphisms. And because these things hold, the order composition that I've defined as fat semi is also associative. So you get all of what you want from that. And the basic diagonal relation is not the identity in this new category, but its weakening envelope is. So the units in my new category are these things that now ought to be called weakening relations. So that's kind of satisfying, and you can identify when a relation is compatible with these new morphisms. Basically, you just need to check these conditions to make sure that you have compatibility, and on the other side as well. So a relation, order relation, is one that's behaving well with respect to this new identity. And those are the things that are the analogs of weakening. All right, so that means we now have two categories of relations. One is using the basic basic relations and composition by way of pullback. That's the B rel, and the O rel category is the one that takes relations that are compatible with the new identities, and in which the fat semi is the composition. And in the concrete case, that's exactly the category. Yeah, it is. Yeah, it is. Right. Yeah, I don't think I have anything on the slide that sort of says that's the case, but it's true. Yeah. Remember that I had that the other direction of this inclusion was always true. But if these things are already compatible with the diagonal, with the smallest weakening relation containing the diagonal, then the other inclusion also holds. So that's useful. So that means that I can compute my composition just using pullbacks. If my relations were already weakening relations, which basically tells you that the original composition is the one you were really thinking about in the first place. So this is kind of a useful technical thing. I don't know if I need to go into too much detail, but basically this says that if I have the opposite of a relation, if I have a cospan instead of a span, so coming this way, then I compute the comma, then upper legs are already tabulating. That thing is already does what I want and is weakening closed and everything you would expect. And now it turns out that so if I take an order regular category A, I compute its category of relations, order relations, then I compute its category of maps, meaning adjoint pairs of relations, then I get something that's identical to the original. That's the main theorem here. So for any order regular category going this way, take its category of relations, take that thing's category of maps, I get back what I want. Right, so that's half of the classical theorem. We want the other half. The other half is the interesting thing, because that's the one that says if I have a category of abstract relations, I can find its regular category. I want the analog of that for order relational categories. So just to remind you, the categories of ordinary tabulated Cartesian bicategory, the tabulated Cartesian bicategories are analogous to the category, or they are the categories of relations, if and only if the Frobenius axiom is. That's what we want. And we want to find, well, what can we replace Frobenius with? Right. So for any Cartesian bicategory, the category of its maps, it already has all of its conical limits. These are special kinds of weighted limits. So they don't include commas, for example. I know I haven't told you what a weighted limit is, but I think half the people in the room know what I mean. And we can kind of wiggle around about it. So it's really the non-conical limits that I'm missing from the picture. In other words, I'm missing things like commas. So how do I get those back into the picture? One, I'm thinking about rel. How do I talk about commas when I don't have the right data to do that? And here's what you do. So what you do is you take for any poset P and any object in my category, I will build a little harness. So what it does is it takes multiple copies of the object A, but it situates them in an ordered harness. So it says this wire, the first wire at the bottom is below the one in the middle, and it is below each of those other two. So this little funny little Y is my poset, and I'm sort of harnessing together these four wires that are all running in parallel. And that is a new object. That's a new wire. That's the idea, right? Now what I want from those wires is that I have for every P, for every element of my poset, I can project one of them at a time. And they need to respect order. So if I project along this wire, that should be above projecting along this wire. So it's not just projection. It's actually this is the cotensor. It's what I'm really trying to build. So I have that relation. That is, for every object in every poset, I have this new object, and I have these new projections. And I also need to have for every function from a poset into a HOM set, I can basically fork all of those into a so this is now a new morphism taking A's into P's of B's that is sort of respecting the order that I specified by my set, by my function S. So this is a little way of building new harnessed gadgets. And those things have to respect some coherence axioms that are kind of clear once you think about what they have to do. And how much time do I have, Marco? Oh yeah, okay, we're good. So here's kind of the main theorem. It's that I have an analog of the classical theorem. Namely, if I have a tabulated Cartesian bicategory, again, that's the original data that we had, minus Frobenius, right? And I replace Frobenius by this. Every object is equipped with this harnessing ability, being able to make these fat wires, these cables. And I have projections out of those cables. And I have ways of bundling parallel morphisms together into cables. Now, all of that data, and they all satisfy the coherence axioms that I just kind of alluded to, then in fact, this runs in the other direction. Start from such a category, make its maps, that will be a regular category, order regular category, I should say. And if I compute its order relations, I get back what I came from. So this is really exactly analogous to the classic. That's the idea. What I think is kind of, I don't know what to make of all of that, quite honestly. It's there. How to think about these things is a little bit hard for me to do. I don't really know. It's not that crazy because in an ordered setting, you should be able to put wires together to build new wires. So this is kind of a reasonable thing to expect. And that's really kind of the main point. I don't have much else to say. There is a little simplification that I'll mention, then I'll just open it up for questions. And that is because posets can be built out of copies of two, and because they are playing a role that's contravariant in this setup. That's a little technicality that I didn't really mention. I should be able to get away with building just pairwise harnesses like this. So basically, anytime I have an object A, I can build a new wire that looks like that. And that basically remembers the order of the two wires. That's really what it does. And that's enough data. I know in principle that's enough, but I don't really know how to sort out the details of how to make that really work. So that's kind of looking at that. I think I can leave it there because I think that's, I'm not mistaken, that's all. Yep. Just wanted to say thank you. So, any questions? Okay, yeah, so Valeria first and then Tiga will come to you.
I don't have a question.
Oh,
I wanted to see that because I wanted to know what we're trying to get rid of. So.
Yeah, this is the axiom that I need to replace because this is the axiom that forces my category of maps to basically to ignore any potential order. Because the maps are the ones that detect order in the first place, right? So that's the category theoretic. You have an object and you know about it by shining lights into it, by shining morphisms into it. And this is the axiom that says no matter how you shine it, you can never see an order. And so we need to get rid of that because we do have order. So the replacement is this idea of putting these harnesses together. I would like it to be a simple wire axiom instead of having to have this harnessing operation and the projections and so on. It would be more satisfactory if I could replace Frobenius with a simple thing like this, but I don't really know how to do that. Tega.
Yes, Drew, thank you for the talk. Now, you mentioned Frobenius axiom. Now, when I think of it, when I look at the category of locales, so I'm asking, you know, we have the Frobenius identity satisfied by the localic open maps.
Right.
It looks to me like this is related to that. Is that so?
Well, yes, it is because the name for it in both places comes from the same Frobenius and the same reason, but I'm not completely clear on how they're related technically.
Okay.
I think they're related historically, but I
Okay.
don't really understand how. And certainly formally, when you look at them, if you write this out algebraically, it really does look the same as the locale open map characterization. Right, you're basically pushing a join across, or rather a meet across the function.
Meet, yeah.
And how it cooperates with its adjoint.
Right.
So yeah, you're absolutely right.
Okay.
It is the same. Formally, it looks very much the same, but I don't really know how they're connected.
Okay, thank you.
Yeah, this is very nice. Thank you. So just to check, the category of partially ordered sets with weakening relations, is it a order regular category?
Yeah, it is.
Okay. And is it somehow at the base of all the order regular categories?
Yeah, that's a good question. I think, well, it is in the sense that order regular categories are enriched over pause. So that's, you kind of can't do this without pause.
Right.
It's also so it's actually the order regular category of the empty theory.
Uh-huh.
Right. So you're asking for no axioms.
Right, right.
Other than the minimum you need for an order regulars. So it might even be the free category. I'm not sure I would want to say that, but it's something pretty close to the free category.
And because of your theorem about the connection with order with quasi varieties, right? So are these basically partially ordered quasi varieties?
Yeah, that's the result of Hertz and Vogel. Yeah, they characterized the order regular categories that have free objects in the right sense as being exactly ordered quasi-varieties.
Uh-huh.
Yeah.
Very nice.
And they also have a definition of exactness, and the exact ones that have free objects are varieties.
Mm-hmm. And just another silly minor comment, but your name order relation is exactly the reason why Valeria has trouble with the concepts, right? It's order relation to me means something different from order relation on your slide. And
So what do you think an order relationship?
it's just a partial order, right?
Yeah, fair enough. Fair enough. Well, yeah, so the title is, I thought about naming it weakening relation, but I thought maybe the audience would not know what I meant by that.
Yeah. No, I understand. And you're
Yeah,
very consistent
right.
with using the order prefix, but you're always going to run into the
Yeah, that's right.
finiteness of the English language versus the number of concepts we want in mathematics.
I'm not sure what my question is, but first, thanks for a really lovely talk and really lovely work. I'm confused about something, but I haven't figured out what yet. Can you go to the definition of, sorry, just an order regular category? I think I saw this.
There we go.
Regular category.
So it really should read analogous to the definition of regular.
It should. Okay. So I'm making some. I'm not thinking clearly, but so order regular implies regular because if you have all finite weighted limits, you have all finite limits. No, it's not. What are we doing wrong here? So and then poset is a order regular category, but not a regular category.
That's correct. It's because the definition of strong and mono need to adapt to the new setting.
Okay.
Right. So you have fewer monos because of that.
Okay.
And therefore you have fewer strong. So
Great. Okay.
that's the issue.
Okay. And then you said nonetheless that you can construct these basic relations in an order regular category.
Right.
And that's even though it's not a regular category, the basic relation construction still works because you still have the fact.
Right. So I haven't thought much about that, but what happens if I do that and then try to recover the regular category that I got from it? Well,
right.
Actually, I don't know that they would satisfy the convenience tax. So
yeah. Okay.
So maybe I've saved myself that worry.
Do you have a sort of, how does cat and profunctors fit into this picture? Is cat some form of order regular category?
Cat itself?
Yes, or some generalization of the structure.
I don't know.
So yeah.
Expect that the analogy would be that I should be thinking about the profunctor category.
Right. Yes. So can you recover the category of profunctors from the category of category?
Seems like I might be able to, but
A common construction, basically.
Right.
Yeah. Okay.
Yeah, this is also somehow related to the fried completion of the category, but I don't really know. I haven't chased it all down.
Hi, thank you. My question is very vague. In order to have the final theorem that you mentioned, you need a lot of extra structure on your category. So how likely or easy or intuitive is to find this structure when you want to work in a particular example?
Yeah. That's not so vague, actually. So if the underlying regular category has cotensors, then you're set. So that's what this star business was about. Now, if you think concretely in posets, what does P star Q refer to? It's the Hom set from P to Q. That's really all. That's exactly what it is, right? So if I have a way, so in semilattices, that's not a Cartesian post category. But on the other hand, if I take a poset into a semilattice, that has a semilattice structure, pointwise. See what I mean? So the morphisms won't be semilattice morphisms. It shouldn't have to be, but they're at least order preserved. And that's what you get. So as long as the underlying category has the feature that functions from pose sets into my objects can be given structure, then I'll have yeah, yeah. But it's a HOM set between a pose set and an object in my category. Right? So as long as you have that kind of pointwise definition, then you're going to be home.
Sorry, this was just a thought in response to your question, Brendan, that when you go to like categories and profunctors, one thing that will break down is that maps in the by category of profunctors are not functors. They're something more general, unless you have some extra. So there are some real there are some fairly fundamental issues that happen, and that's part of the reason why like the Cartesian by category story is so different in the non-locally Posetto case.
Yeah, you're right. That's a really important point because you can't get uniqueness of your functor. So you have to have these weak functors and yeah.
Right. Thanks for the talk. So if you have this kind of situation where you have both functional and relational morphisms between the same things, then sometimes this will give you some sort of power object, right? By lifting relations, functions into the power object.
Right.
So does that happen all the time in ordered quasi varieties? And if so, what are some interesting examples? So for example, I imagine if you start with monoids, you get, I guess the power set of, you get the monoid of upsets. But for example, if you start with the partial ordered group, what do you get? Does this exist?
Yeah, I don't think we know. Well, partially ordered groups are kind of a complication because the inverse is not monotonic. So that's not really treated by this city. But setting that example aside, I actually don't know the answer to your question, to be honest. So, Alex would actually be a good person to talk to about that because we were talking about framed categories, this idea from Mike Schulman's to deal with how do you deal with functions and relations in one setting in a kind of nice, compatible way. A paper of Alex's and mine earlier started dealing with that issue.
Now I do have a question. Because of the stuff that you said about the star being the home, okay. The thing that I think Frobenius kind of reminds me of, it's kind of duplication and anti-duplication, right? You know, you duplicate and then you kind of put them back into one. So it's what's happening here that, you know, if you're thinking logically, we're talking about a system that has monoidal, meaning a tensor product, and a Cartesian product, meaning the Frobenius objects are the ones that are Cartesian monoids, as opposed to being just tensor monoid.
Might be a question for you.
So in the relational category, the monoidal product is not a Cartesian product, but it is Cartesian for the
map,
for the left adjoints, for the maps. Just right. But but you still have one product, but you're saying it acts Cartesian only on a certain subset of objects. So in some sense, it is a similar picture, but it deals with it in a completely opposite way. Instead of having two different products on the same sort of sets of objects, it has one product on two different sets of objects.
Maybe there's a clue. I think this is worth pursuing. There's a clue here that I didn't mention, but if I take this structure and now I replace this splitting and this coming back together with this, make this guy, the one on this side, the one that's coming together, make that a meet operation, and make the other one the adjoint of the join operation. If I'm looking at, if these things are lattices, then the dual of this axiom is distributivity. No, actually, this is distributivity. This is exactly the distributive axiom, which I find really weird. that it's just true. Yeah, yeah. If I take the coming back together and think of that as meaning meet in a semilattice, and I use the fork as the adjoint of the join operation, a lattice will be distributive if and only if it satisfies this axiom. This is a kind of an undergraduate thing that nobody ever says to undergraduates, and they should. It's that a lattice is that's a way of characterizing distributive lattices as a quasi-variety, right? And that basically that's what that axiom is saying. Well, actually, I should have said it a slightly different way, just to make it clearer that it's the same axiom. What do I need to add to this? Oh, I guess I just need to add. What I'm writing is still the same thing, but it's just more obviously the same look. So that's an exercise you can give an undergraduate in a lattice theory course and say, prove that this is the same thing. And now that looks exactly like that wiring. If I replace the split with a join and the merge with meet. Now, if I read it up, it's blue. It's even crazy. Right, if I have this, and I'm guaranteed that I could find witnesses X, then the witnesses give me confidence. So, oh, I know it's cute, and I don't know what to do with it. The what? Yeah, okay. Yeah, yeah, yeah. But what I find weird, and I don't know what to do with it, is that this seems like this is telling me that the discreteness axiom is dual to the Boolean axiom for lattices, which doesn't sound completely crazy, right? But I don't know how to interpret it. Well, right. I mean, these are the diagonal and codiagonal in the bicartesian structure with respect to the monoidal, symmetric monoidal structure. But now, how would I know that an object looks as if it were a semilattice? It would be that this has an adjoint, which would be meet, right? And it would be a joint semilattice if the co-unit, or rather the codiagonal has an adjoint in the other direction. So you can sort of detect when something looks as if it's a lattice in one of these categories by virtue of the existence of this. And then if it is a lattice, then you can detect whether it's distributive or not based on the dual of the Frobenius axiom. I know that's very hand-wavy, but it does work out. Yeah, it's sort of an adjoint Frobenius axiom. Is the Boolean axiom. And the dual of this is always true, right? If I flip the order, that's simply always true in a Cartesian bicategory. And the dual of that is the distributive axiom. So it's only in this direction it makes it no, I guess I've got it backwards. Yeah, I think I said that wrong. One direction is distributivity, and the other, and having that and the other direction, making an equality, is Boolean. Really a complemented distributed lattice. That's what I should put, because the complement isn't in the signature.
I think that we have to thank Drew and Blanche. Thank you.
Thanks.